Okay, right. So as I said, in case the mic didn't pick it up before, this week's recitation is midterm review because this week is your midterm. Hopefully you all know that. So today we're just going to go over some review. We're going to go over the logistics for the midterm, and then we're going to go over some review problems. And I have a few sample ones here in the slides, but I would like, if you have particular questions that you'd like to go over those first. And then we'll use the ones in the slides if you run out of questions. So, a couple logistics. The midterm will be from Tuesday to Friday of this week. The midterm is designed to take 80 minutes. It's designed to be something that would have been possible to take during just a normal class period if we were offering it during class. But we are giving you up to 4 hours to take it. So you have 4 hours from the time that your slot starts to finish the midterm. So time shouldn't be an issue if you are properly prepared. If you have not signed up for a slot online, you should do so now. Professor O'Halloran sent out an email to everyone about signups for the midterm. Make sure you sign up for a slot, because when you show up, you will only be allowed to take it during your slot. Don't try showing up at a time that's not your assigned slot, because we will not let you take it then. If you forget when your slot is, you can go back to that website where you signed up, and it will tell you what slot you signed up for. So make sure you show up during your slot. Now, we actually want you to show up a little bit early. We said 30 minutes early if you can. If you have a class right before and you can't show up 30 minutes early, just show up as early as you can to your slot, to gates 5207. And then from gates 5207, we will tell you which room you'll actually be taking the midterm in, because we have a couple rooms reserved. And depending on which ones are full when you show up, we'll assign you to one that has an available seat. Once you get to the room you're actually assigned to, what you'll do is there'll be a proctor in there, one of the TAs will be in there. They'll ask you to show them your student ID. So make sure you have your student ID with you, and then once they confirm that you are indeed scheduled to take it at that time slot, they will give you a password so that you can start your exam. You'll sit down at one of the computers and type in the password they give you, and it will let you log on to the exam system. So make sure you have your student ID with you. Make sure you show up during your slot so that that can happen. You are allowed to have a note sheet, which can be a double-sided 8.5 by 11 sheet of paper. You cannot put worked out problems on that sheet. So, things you can put on it, you can put, the formula for how to calculate the value of a floating point number, how to calculate the bias. You could put stuff about how to calculate caches, how caches work. You can put that. You can put what assembly instructions do if you want those. But you can't just take an example problem and write out the problem in the solution or the problem in the work in the solution on your note sheet. Okay? Does that make sense to everyone? Yeah?
Can we have code that we use not for just as a reference, I suppose?
What kind of code?
If we needed a certain, maybe an example of how moving works in assembly or something.
How moving works? Yeah, if you want to write some assembly code, as long as it's not like an actual problem, you can certainly have, a move and say, it takes the thing in the first operand and moves it to the thing in the second operand, and the operands are allowed to be registers, or the first one is allowed to be a constant or stuff like that. That's allowed. And also there will be no office hours this week. That was also emailed out. All of the stuff on this slide you should have received in an email from Professor O'Halloran also. But there will be no office hours this week. You can email the staff list if you have questions, but do note that with as many students as we have, responses will be slow to the questions on that staff list. So if it's something where you can find out the answer by looking in the book or the slides, you should do that rather than just emailing us, because we'll probably just tell you to look in the book or the slides if that's actually where it is. And don't be doing it 5 minutes before your exam is scheduled, because you probably won't get an answer before you have to take your exam if you're that last minute. So what should you study? You should study chapters 1 through 3 and chapter 6. The exam will not cover anything other than what's in those chapters, but it will potentially cover everything in those chapters. So that is what you should study. To study, one of the things, is a recommended study method of studying. If you don't know how you want to study for this midterm, try reading the chapter. Maybe try rereading the chapter. Maybe try even reading it a third time. You should work the practice problems in the book. Those will be very helpful. And also, extremely helpful is that we have released previous midterm exams, and doing the problems in those are a good way of knowing if you are ready to do the sort of problem you'll see on your actual midterm. You should note that the online practice exams, the online old exams that we've released, do sometimes contain questions that use the IA32 architecture, so that's the 32-bit conventions. We, starting this semester, are only doing 64-bit, the x86-64. So if you see things that are IA32 specific, you don't need to know the IA32 specific parts of those questions. So, things you might see are like 32-bit stack discipline or 32-bit stuff with a base pointer. EBP was used as a special base pointer. Often, we're not doing that this semester, so you don't need to worry about those particular questions. But anything that's 64-bit from those questions is fair game. You might see similar stuff on this exam. Any questions about that? Okay. So a review of some of the things you'll need to know how to do. So bits, bytes, integers. You should know how to do some basic bit operations by hand. If you see, a shift of, 3 right shift by 1, you should be able to figure out what that will be. You should be able to, do bitwise negation. You should be able to add numbers. You should be able to bitwise AND, bitwise OR, bitwise XOR. You should understand how all of those operations work and be able to do them by hand, because you won't be able to actually, type in code and run it and figure it out that way. But these things might show up where you would have to do them. You should understand the representations of different numbers. So if you have integers, you should be able to say, given an integer with W bits, what's the biggest signed number you could represent? What's the biggest unsigned number you could represent? What happens when we're casting between the signed and unsigned? You should understand all of those rules and know how to figure those out for any number of bits. You should understand the difference between the logical and the bitwise operators. So the difference between the logical AND of 2 values and the bitwise AND of 2 values. And you should understand all of the casting rules. So if you are doing an operation on 2 things that are of different types, so maybe they're different sizes, or one is unsigned and the other is signed, or maybe they're different sizes and they have different unsigned and signed, you should know what the implicit casting rules are and how the operation proceeds. So any questions about that? And of course, these are all things you can write on your note sheet if you don't want to actually memorize them. So of course, you should also know floating point. You should know how to calculate the sign bit, the exponent, and the mantissa from the bit pattern of a number, given a particular floating point format of how many bits we're using for each. And you should be able to then turn that into what the actual value of that floating point number is. Of course, we're using the same floating point standards that we've been using in the book, with the implicit leading 1 for the normalized numbers, and then the implicit leading 0 for the denormalized numbers. So of course, there's the bias. You remember that. This is calculating the bias for a normalized number. We've got the 3 main categories: the normalized floating point numbers, the large ones that are not near 0, the denormalized, which are the small, evenly spaced ones near 0, and then of course the special values, infinity and not a number. And so here's some more stuff about floating point, a little table about the different bit representations and the floating points corresponding to them. So of course, you should remember in the normalized numbers, you've got this implicit leading 1. In the denormalized, we don't have that. We calculate the exponent slightly differently from the bias, depending on if it's normalized or denormalized. And these special values, infinity, not a number, we know we're in one of those. If the exponent is all ones, then we have one of those special values, and what we do is we check, is the fraction all zeros? If it's all zeros, then it's either plus or minus infinity, depending on the sign bit. If it's anything other than all zeros and the exponent is all ones, then it's not a number. Okay, so you should be able to, given a bit pattern, figure out what the actual number is, or if it's one of these special cases, infinity or not a number, and you should be able to go the other way too. Which you did this on Data Lab. You actually wrote code for this. So now we're just asking you to do it by hand, potentially for a few numbers. And then, of course, you should also remember the rounding rules, where if we're exactly between two numbers, we have this special rounding case where we round to even. Okay, so here's an example floating point question, and we'll come back and do this one if we have time, if there aren't questions from you that you want to do instead. Another topic that might be on the exam is assembly. So you should be able to recognize assembly instructions, the ones we've seen so far in class. We've seen moves, we've seen arithmetic instructions, we've seen things like LEA, we've seen some stack modifying instructions like ret and push and pop. And you should understand all of these instructions, what they do in the machine. You should understand all of the uses of registers in a 64-bit system. So you should understand things like RDI will contain the value of the first argument passed into a function. RSI will contain the value of the second argument. That RAX is going to be where the return value is when you return from a function. You should understand, the difference between the callee saved and the caller saved registers. All of that is stuff that you should know. You should understand how different control flow in a C program gets turned into assembly. So what it looks like when you compile a for loop or a while loop or a do while or an if else or a switch. You should understand how all of that maps to assembly. You should be very comfortable with the difference between seeing RAX in assembly and RAX in parentheses. Now that's the difference between saying we want to use the value in the register and the value in the register is a memory address that we want to dereference and use the value of that address. And you should be comfortable with that. You should be comfortable with the different ways that we address memory. So, we have all of these fancy patterns where we've got these different offsets and indices and multipliers, and we have some combination of these. You should understand how all of those work to actually calculate where we're going to dereference in memory. You should understand the difference between Leah and move, all of that stuff. And so then we have, if you don't have questions, we'll go over this assembly loop example in just a moment. Another thing, assembly, you should understand the stack discipline for assembly. So, of course, you only need to know 64-bit stack discipline. This is one of those things where in the old exam questions, you will probably see 32-bit stack discipline questions. The stack discipline was significantly different back then because they didn't pass any of the function arguments in registers. They were all put on the stack, and that made things a lot more complicated and annoying. You don't have to know any of that. Just focus on any 64-bit stack questions you see. That's the convention that you need to know for this exam. Now you should understand how you return from a function, then gets passed into EAX, and then you have a ret. And you should understand these different instructions that modify the stack. So calling, returning, pushing, popping. And another thing you might see on the exam, arrays and array accesses. So you should understand how arrays are laid out in memory. So remember that a 2D array is implemented as a flat 1D sequence of bytes because, of course, our actual memory doesn't have multiple dimensions. And the way we get something in a different row is we have to we go by the width as a multiplier to get to wherever the actual value is. So you should understand how to get the value of a multidimensional array. And of course, this scales. It's the same idea for 3D or 4D or however many dimension arrays you want. Is that we have to scale by whatever amount to get into this flat 1D array. Okay, so something you might see on the exam would be something like this, where we give you some C code that says we're going to do this array operation. Here we're just taking some value in array 1 and assigning it to a location in array 2. And you're given some assembly, and this assembly is the compiled version of this, and we ask you to find what the actual values of H and J are. So the dimensions of the array based on the assembly that was used to do this assignment. This is something that you should know how to do, and you'll see, this one is from fall 2010. You'll see in the old exam problems examples of these to practice. And we can go over that one also if you don't have any questions. Caching concepts. So you should understand how caches work. Hopefully you learned that in Cache Lab when you wrote your cache simulator. You should understand, though, the number, how caches are divided up into sets, and each set has the sets have some associativity. The whole cache has an associativity, which is the number of lines per set. That each cache has some particular block size, and how we can calculate the whole size of the set from that, or the size of the whole cache from those numbers. How we can find out where an address is in the cache, if it's a hit, a miss, if we have to evict something. You should understand hit rate, miss rate. You should understand sort of how we can make design decisions in our caches that allow us to avoid particular types of misses, and what parameters we would tweak to get that. So that's sort of like, this is the idea of, by changing your associativity, if you change, from a direct mapped cache where there's only one line per set to a fully associative cache where all of the lines are in one big set, this changes our misses, because in the fully associative cache, we only have a miss when the cache is completely full. Or we only have to have an eviction when the cache is completely full and we have a miss. Whereas with the direct map cache, we might have empty space in our cache and still evict things if they're in the same set. Does everyone understand that? Okay, and that you can refer back to the Cache Lab slides about the the cold miss, the conflict miss, the capacity miss, the different things we had. Okay, so what we're going to do now is, for the rest of the recitation, we're just going to go through practice problems. And so I have the couple that are already in here. Actually, before we do that, I just want to, one more note is, anything in chapters 1 through 3 and chapter 6 is fair game, even if it's not in these slides. These slides are an overview, but they're an incomplete overview of things you might see on the exam. Anything in those chapters might show up on the exam, even if it's not something that I mentioned in these slides, okay? So just to let you know. But for the rest of the recitation, I just want to go over review problems. So before I go over the sort of the pre-planned ones I have in these slides, are there any particular topics, questions, review problems that any of you would like to go over or see? Yeah.
Kind of if you have structs and you're padding, and you're doing padding.
Right.
So if you have a char array, will you ever need padding before that?
So do you ever need padding before a char array? Yeah. So a char array, is just a bunch of chars. And since chars are 1 byte aligned, then it's okay to put them wherever you want. Right. So that one will be okay.
And if you have a struct within a struct, let's say the struct you have within the size of 6, so it has an int and a short.
Okay.
Would you still consider it to be size 6 in the sense of padding, I guess?
So the struct itself needs to be aligned to the size of its biggest member. So if if the biggest thing in the struct is an int, then the struct itself needs to be aligned to a multiple of 4. Any other questions? Yes?
Let's go over finding the percentage of hits and misses.
Finding the percentage of hits and misses, okay. Is there a particular example you had?
Question already. Just basically passing. Some fun
Okay, yes. So can I take this? Okay. Okay, so here's an example problem. This is from one of the old midterms. It's on the website, right? Is that where it's from?
Yeah.
Yeah, okay. So this is an old midterm question. Okay, and it's about caches. And so it says that we have a cache with 512 bytes. So the size of C is 512 bytes. Okay. And we know that the cache is LRU. Eviction policy least recently used. That's the one you implemented in your cache simulator. And we know that the cache is initially empty. Okay. So that's our setup. And we say that we send the following addresses to the cache. So we're going to send it 02481632. So we send it 02481632.
Is it a fully associative cache?
Let's see, assume. It doesn't seem to say. So here we
Which year is the exam?
This one is fall 2011, exam 1. This is fall 2011, exam 1, problem 8. Okay, it doesn't seem to say what the associativity is. Maybe we don't need that. And okay, so we get the address. These addresses are sent to the cache, and the hit rate is 0.33. So let's see. So we sent 1, 2, 3, 4, 5, 6, and the hit rate is 1/3. So that meant that we had 2 hits and 4 misses. So that's the first thing we figured out. That wasn't given to us. We just figured that out from the hit rate and the number of addresses we sent. That was just a little bit of simple math. Hit rate times the number of accesses is the number of hits, and then, of course, the rest must be misses. And the question is, what is the block size of the cache? Okay, so what is the block size of the cache? Okay. So let's see. So let's see. So we know that we can move over to the caching slides while we do this. Okay, so what we know about a cache, so we know that the size of a cache is the number of sets times the associativity times the block size per line, right? So that, sets times associativity is the total number of lines, and each has block size bytes. So we know that 512 is going to have to be equal to the number of sets times the associativity times this block size, okay? And this is what we're trying to solve for. So the block size is going to be equal to 512 divided by the number of sets times the associativity, whatever that ends up being. Okay. And so now we want to figure out what this is. And then we'll have B, okay? So we know that we had 2 hits in this pattern and 4 misses. So what do we do? Cache is initially empty, so it's obvious that this is going to have to be a miss because the cache is cold. We know that one. Okay, and oh, actually, we do have some options. We know that our options are either b equals 4, b equals 8, or b equals 16. So our options are b equals 4, b equals 8, b equals 16, or none of the above. Okay, so this is nice that we actually have, now only sort of 4 things we have to test out. Does anyone have any ideas on what we could do now to sort of figure out which one of these it is?
0 to 4 are the addresses. Oh, they know.
These are the addresses, yes. So they're very small addresses, but these are the addresses. Okay. Any ideas on what we could do given the fact that we actually only have 4 options? That would be reasonably quick here. Yeah, we could just like say, okay, let's assume it's 4. What are the hits and misses going to be? Let's assume it's 8. Let's assume it's 16. And see which one of them ends up with 2 hits and 4 misses. That actually seems like a reasonable thing to do. Because, there's only 3 things we're going to have to try out.
Is it multiple choice in the show?
Not every question is going to be multiple choice, but there might be multiple choice questions on it. Yeah, I'll say that. I mean, this is an old midterm question, and it happened to be multiple choice. In general, though, this sort of strategy of we've narrowed it down to some set of options, and now we can just test them out is something you can use, even if it's not multiple choice. If you ever got in a situation where you could say, well, I know it's going to be either this, this, or this, and I'm not sure which one, try them out and see which one works. Works even if it's not multiple choice, if you can get it narrowed down to a small set of options. Okay, so let's see, what would b equals 4 do? Okay, so b equals 4. The cache is 512 bytes. Then if b equals 4, then s times e is going to equal what? 512 divided by 128 equals 4, is that right? Yeah, okay. So s times e is 128. So what does that mean? Yeah, definitely, it does not say anywhere what our e is. Yeah, so this is all we know. What?
Can we just use the blocks that you see which ones are? Yeah, you don't need S and E, right?
Oh yeah, do we not need S? Oh, okay, yeah, we don't even need S.
2 would be a hit with B equals 4.
Right, yeah,
4 would
okay.
be a miss.
Yeah, with b equals 4. Right.
Miss,
Hit, miss,
hit,
hit,
miss, miss.
miss, miss.
Yeah, so that's the answer.
Okay. So yeah, so that looks like it ended up being 2 hits, 4 misses. Okay, that's good. Okay, right. So what we said was the block size is 2, or the block size is 4 bytes. What's going to be in it? So we miss on 0. That loads up 0, 1, 2, and 3 because it loads up 4 bytes. So 2 is loaded up, so that's going to be a hit. 4 is definitely not loaded up, so that's definitely going to be a miss. See, but is this actually a hit?
Oh, wait.
Right.
I don't know.
I think that's a hit.
Right, yeah. We loaded up 4, 5, 6, and 7. So then 8 is actually also a miss. 16 is a miss. 32 is a miss. Okay, so this was actually 1 hit, 3 misses. So we were slightly off. Okay?
5 misses.
1 hit, 5 misses. I can't count.
5, 6, 7.
Right, yeah. So does everyone see why 8 was actually a miss? Our block size is 4, so that means the first block is 0 through 3, and the next one is 4 through 7, and then 8 through 11 is a different block. Okay? So that was with, 4. Was 1 hit, 5 misses. Let's try it with 8, because, this obviously didn't work now, we see. So what happens if we have 8? The first one's always going to be a miss, because the cache is initially empty, right? Can't possibly be in it. And then that loaded up what? That loaded up 0 through 7. Right, so 2 is in there, 4 is in there. Now 8. Is 8 in there? No, because we loaded up 0 through 7. So 8 is a miss. Is 16 in there? No, because when we loaded up 8, that loaded up 8 through 15, because the block size is only 8. So that's a miss. And the same thing here, 32 is not in there. Okay, so that gives us 2 hits and 4 misses, which is what we are looking for. So it looks like B is the answer. We could, just to double check, look at 16 and make sure that, that comes out to something other than this, so that, we can be sure that we actually did get the right answer. If we did 16, let's see, 0 is a miss because the cache starts empty. Then what happens? Well, we loaded up 0 through 15, so we're going to see, okay, all 3 of these hit. And then this is a miss, and then this is a miss, because that loads up 16 through 31, and now 32 is a miss, but that's 3 hits, 3 misses. It looks like the one that gives us our hit rate is indeed B equals 8. So yeah, so there we saw that, okay, we were thinking about like sets times associativity. We didn't actually need that. That's why the problem didn't tell us what the associativity was. It didn't even matter. We didn't need any of this. What we really needed, actually this, the fact that it was 512 bytes isn't even useful. All we care about is that it's big enough to hold, one block, which it better be. And then we were able to figure it out just by plugging them in and looking at what happened. So that was good. It gave us a little bit of information that wasn't, actually something we needed. We went slightly in the wrong direction at first, but then we realized we could just look at the block size and look at the patterns and use this hit rate to figure out which one of them was the one that matched it. And since there was only 3 to check, that was fast enough. Hopefully you can do that when you have 4 hours. Okay, so are there any questions about how we got B from this problem? Yeah?
So it's able to load up the amount based on the block size.
Right, yeah. So every time we have a hit, it loads that whole block into the cache.
And we're kind of assuming like each int is like just one of those, like the next 4. Like say your block size is 4, it can like each of them falling into this can fit in one of those blocks.
So, well, yeah, so these are actually bytes. So we're saying the block size is 8 bytes, and the addresses we gave it are byte 0, byte 2, byte 4, byte 8. Right, so, if these were integers, then, the first integer would actually be all of this. So it looks like we're not doing integers because we're getting something at offset 2, which would be halfway through an integer if we were doing integers. Any other questions about this? Okay, so there is Fall 2011 problem 8 solved. Are there any other questions? Yeah, okay.
There's a question in Fall 2012.
Fall 2012.
The 6th question.
This is Fall 2012. Number 6. Yeah, if I could see the question. Okay, so this question is, so this is about structs. Okay, so this is a long one. Okay, so we've got struct confuse. That's the name of the struct. And in it we have char systems long theory. We have another struct in it called applications. And in that struct, there's a char array of size 3 called web. And this struct is named database inside our outer struct. And we've got an int pointer called languages. And a pointer to another struct confuse. So that, I guess it's like a linked list of these things. And that one's called math. Okay, so this is quite the confusing struct, as its name suggests. There's lots of stuff in it. Okay. And then what we have is we have 3 code blocks and 3 pieces of assembly, and we want to match up the code block to the assembly function.
Can you just open it up on that?
Oh, actually, that would probably be faster. If I can find it. Yeah. Actually, let me just give this back. Yeah, let's open it up. So this is fall 2012, exam 1, number 6. Okay, so there's the problem on the screen. Okay, this is better. So there's the struct. We just wrote down. And what we have is we have these 3 pieces of C code, and we've got 3 pieces of assembly code, and we just want to match them up. So we want to say which piece of C code belongs to which piece of assembly code. And we know that one of them is each of those. It's not a trick question. But okay, so what does our first piece of C code do? So our first piece of C code is going to take a struct confuse pointer, and it's going to give us back a character pointer. And the way it does that is it's going to return the address of the second element of the array, this array in this struct in here. Okay? And one of these offsets is that offset that does that. So what we really need to figure out here is, where in memory these things are being stored, where they are in relation to the beginning of this struct confuse, because we get passed in the pointer, that's the beginning of it, and we need to figure out which one of these is going to be those locations. Okay? Does that make sense to everyone? How we're doing that? Yes? So, okay. So are there any of them, even before we do that, that maybe look like we can sort of get away and maybe not figure out what the actual answer is? Yeah.
B does a load effect address while the other 2 can use. So we can basically figure out that B is going to be the one that returns an address.
Right, okay. So it's looking like B returns an address, which bachelor's does that. So we're trying to match up A, B, and C. So it looks like, B returns an address, and of these 3 functions, that's the only one that returns an address. So we're thinking that maybe this one is bachelor's. Okay, and then let's see if we can sort of get guesses for the other 2 the same way, and then we'll go and check them and see if they make sense and where they index to. Well, let's see. So what do the other 2 do? One of them is going to return the value, and the other one actually does a dereference. Okay, so which one of these do you think is the one that does A? One does a dereference and the other doesn't. So do we see in the code something?
One B or masters B thing
Masters B A.
RAX.
So okay, so that's dereferencing. This one looks like it dereferences too, though. So maybe
Is there a difference, or is there any significance in the fact that the first one uses RAX instead of BAX?
okay. So this one is moving into a 64-bit register, and this one's moving into a 32-bit register. So let's see. So pointer languages. What's languages? Languages is an int pointer. So when we dereference it, we'll get an int, which is 32 bits, right? So maybe then, since this is putting it in EAX, maybe C is masters is maybe our guess. And then that would mean that this one, which puts in a 64-bit register, returns theory. What's theory? Theory is a long. Okay. Yeah, that would make sense. Okay, so these are our guesses. So this is what we think. No. Think maybe that these are what it is, just based on the fact that we saw, oh look, we have address of, we've got dereference, we can look at the different sizes. Was there a question? No? Okay. So these are our guesses, but was there a question over there? These are our guesses. What we'd like to do is actually go and look at where the offsets are and double check that we got the right ones, just to be safe, because we have 4 hours for these exams, so why not? Maybe if we were actually taking the exam, we'd put these down and then come back after we finished the rest of it to see that these actually match up. If we're reasonably certain that we got it right based on just that little bit of information, then we'd come back and check once we knew that we had time remaining. So okay, so what do we do? So we're thinking that maybe A is PhD. Okay, so PhD goes to math. And then from math, it goes to theory. Okay? So where is math going to be in this? So we sort of need to figure out how this is laid out in memory. So this is, a char is 1 byte. So the size of this is 1 byte. So this is just going to be, at an offset of 0 from the start of the struct. Along here, okay, so are we doing, we're doing that along is 8 bytes. Is that what we're assuming? Does it say? Yeah, okay, so I think we're assuming that long is 8 bytes here. So this needs to be aligned to its size within the struct. So if the long is 8 bytes long, then even though we have just a char here, we have to wait until we get to the next multiple of 8 to put this down. So these are offsets from the beginning of the struct. Okay, so then we have a struct applications. And what's the biggest thing in it? The biggest thing in it is just a char array. So it's just got some chars in it, so it can be aligned to wherever. So this was, that's not 8, it's 10. Okay, so this was 8 bytes long starting at 0x8. So that takes us to 0x10 as the start of this struct. And that's, okay, then we've got an int pointer. So an int pointer, we have to align it to another multiple of 8. So this is going to take less than 8 bytes. It's only 3 bytes. We'll have extra space because we need to align this to a multiple of 8. So it's going to be at an offset of 0x18. Do we see how we got that? Yeah?
Why is theory not at an offset of 1? Because it would be 1 after systems, right? So like 1 byte and then theory.
So the thing is, each element of the struct needs to be aligned to its size. So if this is 8 bytes, it needs to be aligned to a multiple of 8. And that means if we're not already at a multiple of 8, we just add padding until we get to the next multiple of 8. So what happens is we have this character, and then we have 7 wasted bytes, and then we have the long, and then we have the struct. Okay.
So when we do this kind of question, do we assume that we align those elements without optimization?
Yeah, so you should assume that the compiler didn't rearrange the members of the struct to optimize. Assume they're laid out in the struct in the order that they were given. Because of course, yes, the thing is, if you sort them by size, putting the biggest to smallest, then that will optimize the use of space. Is a property they mentioned in class, probably. Okay, and then what's left is another pointer. So what do we get? We get here x1. Okay. So, 8 more bytes after this pointer, that's a multiple of 8, so that's okay. So then, okay, so we said PhD was probably A. So we did pointer to math to theory. Okay, so we went by an offset of 20. Yeah, that takes us to our struct pointer. And then from there, we went by another offset of 8. So yeah, so that takes us to theory and the other struct. So it looks like we got this one right. Cool. Our guess worked out. Do we see how we got that? Yep.
RDI stores the address, right? So why would we dereference it before adding 0x20?
So what we did is we went to an offset of 20 from RDI. So RDI is the argument to the function,
Yeah,
the
but
pointer to the struct.
with the brackets, right?
That gave us a struct pointer.
No, I got that, but I mean RDI itself is an address, right?
Mm-hmm. Yep.
So why would you
We want the value at an offset of 20 from the pointer RDI. We want this value. We want the value of the pointer, not the address of it, because we need to dereference it. Does that make sense? So we get the address of the pointer, and then we dereference an offset of 8 from that to get theory. That gives us PhD. Okay, so now we're double checking that B was bachelor's. Okay, so what did bachelor's do? It got the address of the second byte of database. So what did we do? We went of an offset of 12. So 10 takes us to web 0, and then web 1. So that's web 0. Web 1 would be 1 byte more from that, which would be 11. 1 byte more from that would be web 2 is 12. And that is indeed what we put in. So, and we just got the address of it rather than the value at it because we used Delia. Okay, so that looks good. It looks like we found the address there for bachelor's. And then it better be the case that master's is right at this point. But we can even look and check just to make sure that we got it right. What did we do? We said we want to find languages, and then we want to dereference that pointer. So, okay, so we went to an offset of 18 and got that value. Okay, so the offset of 18 was languages, right? And then we dereference it and put that into EAX. So, as an int star, we dereference it to get an int, put that in EAX and return. So it looks like that is also what we did for masters. So we've double checked. It looks like we got it right. This is the correct order. Everyone see how we got that? Okay, good. This was on my midterm, by the way, when I was in the class. I remember it now. Okay, oh wow, it looks like we're actually out of time. Any other quick questions before we finish? Yeah.
How do you tell when LEA is being used for arithmetic versus for progress?
You sort of have to look at the context. You can't just, the instruction itself looks the same on just that line. You have to look at the context to see how it's being used. Of course, if you want to try out the other practice problems in the slides, you can try those out. Try out the other exam problems.